Nice work, Ed. We're supposed to be heading for the center of the galaxy, not spinning around here. Better contact Capcom for course correction.
Oh, come on, Charlie. We can figure this thing out ourselves using trig functions. Let me get it up on the screen here.
Okay, Ed, let's try it. Now, according to our flight plan, we need a course that's in a direct line with GeoSat 4 and Capcom.
So all we have to do is find the number of degrees we're off course, then swing around by that angle and head straight out from there.
Uh-huh. So what's the angle?
I don't know. I think I'd better put up the help screen.
In the last program, we looked at angles on the Cartesian plane and defined r and the trig ratios using coordinates. Now let's look at a special case. Here, the terminal arm rests on the y-axis with theta being 90 degrees. R can be any length. We've picked point 03. Notice that R is equal to the y-coordinate 3. The trig ratios are 1, 0, and undefined. Also, notice the difference between dividing 0 by a number and dividing a number by 0. Let's pick a different point. Because the value of x is 0 at 90 degrees, r will always equal the value of the y-coordinate. This means that the sine of 90 degrees is 1, the cosine is 0, and the tangent undefined. Another special case occurs when theta is 180 degrees. At first glance, it appears that r is -4, but because we square the x and y coordinates, r is always positive. We can also find r when theta is 270 degrees, or 360 degrees. While r is always positive, the trig ratios can be negative. For example, in quadrant 2, sine is positive, but cos and tan are both negative. If we examine probe 1's position on the Cartesian plane, we find that it's sitting at point -46 in quadrant 2. Let's use probe 1's dilemma to demonstrate that calculators simply cannot cope with every situation. First, we calculate r using the Pythagorean theorem. We know the sine of theta is y divided by r, or 6 divided by root 52. Now, let's make a triangle and examine angle alpha. The length of AO is 4 units, and AP is 6. Since APO is a right triangle, the sine of angle alpha is opposite over hypotenuse, or 6 over root 52. This is the same value we found for sine theta. Therefore, sine theta must equal sine alpha. There is one other relationship we need. The two angles, alpha and theta, together make 180 degrees. So, alpha equals 180 minus theta. Looking at the two equations, we see alpha in both. Substituting for alpha in the upper equation, sine theta equals sine 180 minus theta. Now let's find a cosine relationship between alpha and theta. We know that cos theta is x divided by r, or minus 4 over root 52. Again, if we drop a perpendicular, we have right triangle APO. So cos alpha is 4 over root 52. If we multiply both sides of this equation by minus 1, the right sides of the two equations are now equal. Therefore, cos theta must equal minus cos alpha. We already know that alpha plus theta equals 180 degrees. And therefore, alpha equals 180 minus theta. Substituting for alpha, cos theta equals minus cos 180 minus theta. Now let's use the trig ratios to find angle theta. We know the values of x, y, and r, so we can apply any of the trig ratios. Sine theta is 0.832. Using a calculator, we find angle theta equals 56.3 degrees. But wait a minute, something's wrong. Angle theta is obviously greater than 90 degrees. So much for the calculator. Well, earlier we found that sine theta equals sine alpha. So the 56.3 degrees must refer to angle alpha. But we wanted the value of angle theta. Alpha and theta together add up to 180 degrees. So theta equals 180 minus 56.3, or 123.7 degrees. This is the angle the boys can use to correct their course.
See, Charlie? I told you we could work this thing out using trig functions.
Probe one, what's your status?
Everything's under control, Capcom. All we have to do now is stay in this orbit, swing around by 123.7 degrees, and we're back on course.
Nice going. Now no more side trips, eh, boy?